Good day. This is Module 2 presenting vector operations, that is solving problems involving vector projections. So we have here the following problem. If line L is a line in two space or three space that passes through the points A and B, then the distance from a point P to the line L is equal to the length of the component of the vector that is orthogonal to the vector. Use the method above to find the distance from the point P, whose coordinates are negative 3, 1, 2, to the line through the point A with coordinates 1, 1, 0, and point B with coordinates negative 2, 3, negative 4. So in this example, we're going to apply the definition given above and also some formulas that we need to recall. And that is, we have the vector projection formula. So this involves defining the distance between the point P given and the line AB. So if we're going to look at the figure here, any of these two figures, we can say that we can apply the formula of vector projection because the distance that is needed to be found is actually your W2. And this W2 is, we have it as the vector component of U orthogonal to V. Then we are given point P and also the line segment which is perpendicular to W2. So same thing when we have the situation on this figure. Still, we're going to find the distance that is represented by W2 from a point P and along a line L. So with that, we have here the formula. So the formula to be used is for the projection of U onto V, that is equal to U dot V over magnitude of V by D squared times V. So this is the projection of U onto V by the point P on your line AB. So let us work now on the problem. So let us point the 3 points given so that we can illustrate the situation of the problem. So we have here given point with coordinates negative 3, 1, 2, then the 2 points given A and B. So plotting these 3 points on the X and Y coordinate system. So we have this as your X, Y, Z coordinate system. Then let us plot the point P negative 3, 1, 2. So X is negative 3. So we plot along the extension of your positive x-axis. So first is negative 3, then 1 unit to the right, then 2 unit upward. So this is now the location of your point P, whose coordinates are negative 3, 1, 2. Then for your point A, you have it as 1, 1, 0. So x is 1 unit, y is 1 unit. So this is your point A because z is 0. So let's have it as 1, 1, 0. Then for your point B, which we have the coordinates negative 2, 3, 4. So that means it is on the negative x-axis. So that's it. For negative 2, then positive 3. Then you have 4, rather negative 4. So we have negative 2, then positive 3, then negative 4. Suppose this is now your 2 points, A and B. So let's have these points now drawn. So this is your line AB. Then this is your line P. And we're going to find the distance now from the point P to the line through AB. So we're going to find that distance. Okay, so from what we have here now, let's have AP denote as our U, or I should say this is the distance. So let's define the two vectors that we need here. So this is point A, connecting it to point B. That will now be the vector U. So let's connect it. So it is difficult because let's say this is your vector U. So it's like what we have in the drawing a while ago, that you have this as your vector U, projection of U onto V is this one. And this we have it as the line segment AB. Then we have this as point P. And we're going to find the distance here. So of course, when you find the distance here, we use by Pythagorean theorem concept. And that is equal to, so distance by Pythagorean theorem. And the formula is equal to the square root of magnitude of U squared plus the magnitude of the projection of U onto V squared. So what we will do now is to find vector U. So the vector U can be found by the line segment, which is AP. Okay, so that's line segment AP. So I just projected it here so that it will be bigger triangle. This is a very narrow triangle. Okay, so let's have this as point A. So with that, component of your vector U is, you get the distance of your AP, or the components of your vector AP. So being A as the initial point, terminal point is P. So we have here -3 minus 1. Then you have 1 minus 1. Then 2 minus 0. So vector U will have -4, 0, 2 as the components of your vector U, or line segment AP. So we will need to get also the line segment AB. The line segment AB, which is also your vector V, because this is your vector V, based from the illustration that we have a while ago. And that vector V is represented by, again, line segment AB. So getting down the components, so initial point is A, terminal point is B. So that's -2 minus 1, 3 minus 1, then -4 minus 0. So therefore, vector V will have components. Negative 2 minus 1 is negative 3. 3 minus 1 is 2. Negative 4 minus 0 is negative 4. So we can now compute for the projection of U onto V. Projection of U onto V. Particularly, the formula is quantity U dot V over magnitude of V squared times V, based from the formula that I have shown you. But we can still get the projection, magnitude of projection of U onto V based from this formula of distance. So we get now the magnitude of projection of U onto V, and that is equal to U dot V over magnitude of V. So this is again taking the magnitude of projection of U onto V. So we have here now the simplified formula. So with that we now have projection of U onto V equals U dot V. So let's get the product. U dot V equals, we have negative 4 times negative 3 plus 0 times 2 plus 2 times negative 4. So U dot V equals 12 minus 4 is, rather 12 minus 8 equals 4. So that is now 4 over the magnitude of V, that is square root of quantity 3 squared plus 2 squared plus negative 4 squared. By the way, this should be negative 3. So the answer for the magnitude of V equals 9 plus, we have this as 6, 4, and 16, the square root of 29. So this is square root of 29. So we have found already projection of U onto V. Then let us also find the magnitude of U. For the magnitude of U, so that is equal to, you have 16 plus 0 plus 4, that's square root of 20. So with that, we can now define the distance to be equal to magnitude of U squared, that is square root of 20 squared, that is now 20. So you square that, then you also have to square this, that is 16 all over 29. By the way, this is distance, so it should be minus. That should be minus. So with that, the answer here would now be square root of 564, when you simplify it, over 29, or equal now to 4.41 units. So that's the distance from the point P to the line AB.